The shallow diameter gauge. We're going to be looking at some of the machining that goes into making one of these, and mainly focusing on the more unusual aspects of that machining. We're going to gloss over some of the conventional machining and grinding. Because this is such a challenging thing to make, I also felt it important to come up with a 3D printable design. So this design just uses some off-the-shelf hardware from our favorite online vendor and snaps right together. And it gives pretty good performance, all things considered. So you might ask, what is a shallow diameter? It could be an inside or an outside diameter, but the core theme is the length of the diameter's land is too short to measure traditionally. So this outside diameter with its 100th thou length can't be measured with a traditional micrometer. And you say, well, caliper could get on there. Yeah, but if you're trying to hold seal fits or bearing fits, caliper really isn't what you want to be using. And then on this inside diameter, there's an embossment preventing something like a traditional plug gauge from being used. So a shallow diameter gauge can measure all three of these diameters, no problem. And it can also do some things you wouldn't think about, like tapers. It can measure face and taper contacts, like on a lathe chuck. It can do grooves, both face grooves and OD grooves, and it could do all kinds of lengths and really very universal type of gauging, and I wouldn't want to be without one. So I hope you get something from this video. Let me know. So here is the gauge I drew my inspiration from. This is a Federal shallow diameter gauge. They're no longer in production, but my past employers and I have all liked these so much, I've actually made quite a few reproductions of these. And one of the things I've discovered is that this slot that runs the length is a liability in terms of getting this bottom plane flat. So when I made mine, I got away from the slot, and instead I have a through hole with a tapped hole on the opposite side, and then the carriage is slotted. So the carriage can still be adjusted, and then you just tighten the screw to locate it. My other issue with it is the carriage floats a little bit when you go to lock it up, and it can make setting the probe depth a little challenging if you need to hold a very specific depth. Sometimes you might have a counterbore as shallow as a millimeter, and so if your carriage is floating around half a millimeter, that could be a little frustrating. And then my final issue with it is it takes 2 Allen wrenches to both adjust the carriage and the probe height. And so on mine, I unified everything to one 2.5 millimeter Allen wrench that handles all the adjustments for the entire system. Otherwise, it's just a few DFM things. Instead of a stack up of 3 basic plates, I went with one more complex one. With the advent of CNC, lower, more complex part quantities I find to be easier and cheaper than lots of little simple parts. But it really kind of depends on your shop. If you're a manual shop, maybe this makes more sense. But yeah, otherwise, very loosely inspired. Another thing I changed, instead of the wood insulator grips, I just 3D printed them. And if anything, the hollow infill nature of 3D prints makes for a pretty good insulator. On top of that, I think it looks pretty sharp too. So this is the CAD model for the gauge. We're going to take a look at each piece and briefly see how we manufactured them. We're going to start with the main frame of the gauge. So if we take a look, it's pretty prismatic, just a lot of holes, and then the only thing of note is this T-slot. We did have to hard cut that feature, and hard cutting T-slots is a little tricky, but it works well enough. The only design for manufacturing issue I had is this M2 screw hole, which was too deep for my traditional thread milling solution that I used on the top M2s. So I did have to hand tap that one. Otherwise, pretty straightforward. I gloss over the grinding of it because we established in past videos how to grind things flat and parallel, and so I just really wanted to quickly focus on the hard milling and things you can do, like try to avoid deep holes like this. This is the M2 tap I was talking about, having to hand tap. Had I got this from a customer's engineer, I'd complain all week, but since I designed it, it wasn't that bad. Just a quick look at grinding this up. Again, just kind of wanted to gloss over it. I used the same technique I used for the thin V block. This is the hard milling. I had to do it in the Haas since it is slightly too long for the Mori, but I'm using a step down technique with a back tapered end mill. And so even a machine like the Haas can still deliver pretty good results because the cutting pressure is so uniform. For the gauge frame, some of the fits we have to be cognitive of is we don't want this end cap floating around and sitting lower than the bottom face. And so how we prevent that in order to keep this slightly above is we hard milled two 2mm dowel holes into the frame, and then on the end cap we have two 2mm posts, which are H7 and fit into that dowel hole, and that just keeps everything aligned. Some of the other fits we have to worry about is we don't want this flexure spring here being out of perpendicular to the face of the part. And so how we keep everything nice and squared up is on the frame, we have a slight slot that the flexure spring sits in, and it just slip fits into there, and that keeps everything aligned pretty accurately. Same goes for the contact moving carriage. We have a 5/10 gap between this face, and the carriage, and then also we have the widths at 5/10 over gap, and that gives you a nice running fit with minimal wiggle. And then also we have a slip fit between the gauge and the indicator adapter, because we want the indicator, if we have to adjust it, we want it to maintain perpendicularity to the contact. So that's the gauge frame. Moving on from the gauge frame, we can look at the adjustable carriage and then the floating carriage. So on the adjustable carriage, we do have this gear rack and then a small brass gear, and a 2.5mm Allen wrench goes in and it makes this move side to side, and that's how we set the position of this fixed contact. So the gear rack, will mill that in, and we'll also mill the brass gear, and then that gear is held in place by the indicator mount and a small pocket we milled on the gauge frame. So I thought that was kind of a clever way just to keep that gear in place with minimal hardware. And the other thing to note on the carriage is I wanted a low profile way of securing the probe from the side. And so what I did for that is I just have these two discs with a chamfer on it, and then when you torque the chamfer, they lock up in the bore they ride in. And that works pretty well. It allows side access, it clamps very securely, and so that's the fixed carriage. And then over on the floating carriage, same implementation, just a 6mm hole, and then these two discs with a chamfer to lock everything up. More 2mm holes. These are all a lot easier. And then I made two holes through here just to make assembly a little easier. You could pass a wrench through and secure these. And then a set screw with a slit and a locking screw to secure it for adjusting the zero on the indicator. And those are the carriages. And then the flexures, they get milled from from shim stock, spring steel shim stock, using a super glue method a watchmaking friend Josh Hacko taught me. So we'll go over that too. This is the super glue work holding technique. It starts with a pallet that has some V-grooves grooved into it on a fairly tight pitch. Mine's 2.5 millimeter, but Josh actually goes a little tighter on his. So you prep everything clean. I've had to deburr my shim stock material. Now I'm just priming it. And you'll just put down a pretty large layer of glue. And what happens is the grooves, the excess glue pours into the grooves, and it gives your part very intimate contact with the top face of the pallet, yet the grooves allow enough glue to still hold it securely. So you don't get a uneven parallelism like you would without the grooves. So just kind of seat it and then put some weight on it and let it cure. And I let it cure overnight. I'm in no hurry. So the next day, we could start machining. So we're just using a 1.5 millimeter end mill at 24,000 RPMs and kind of interpolating out all the screw holes. And then we'll do some 2D contours to cut these out, stepping down 0.1 millimeter at a time. I should say this is a 10 thousandths or 0.25 millimeter thick blue temper shim stock. So after the machining is finished, we'll just submerge the pallet in some acetone for up to a day or two, however long it takes, and that'll demount the parts and the extra sheet material from the pallet. The other nice thing about the grooves is it kind of gives a route for the acetone to enter underneath the sheet, and it demounts a little bit quicker than a part without the grooves under it. This is the machining process I'm using for the circular clamps. I just part them off, send them to heat treat bundled so they don't get lost in the oven. Then post oven, I'll grind the chamfer on. It's about 50 thousandths deep when turned on its side, and I'll just plunge that down and then move down a few more tenths and then walk the wheel off. And that'll produce a pretty nice finish. And it won't really pump a lot of heat into such a small, delicate part. Using the same part-off method for the little clamps that secure the flexures. And then doing a little bit of cleanup. A little bit of the tab is still on them, and I'll just use some low-profile side cuts to remove it. And then do a little manual deburring, and then we'll stick them on the surface grinder and remove what's left of the tab. So oftentimes on small parts like these, only a few surfaces really need to be precise, but it would be in poor taste to leave the remaining surfaces unground. It wouldn't look all that great, and so you want to come up with a way to very quickly remove the material and put a ground finish on these surfaces. And what I use is called peel grinding, and so you could take like up to a 5,000 step the cut without much penalty. So I've established the top of the part, and now I just have to figure out where the rear corner of the wheel is, and I'll test cut up against a shoulder, measure it, and then adjust. And once I have the wheel located, I can essentially just follow the path of the part, like a 2D line almost, like a lathe would, and produce very quickly a very acceptable looking part. So the thing with peel grinding is you can't take a very wide step over. It's usually in the order of about 1/2 of a grain. So I'm running a 60 grit wheel, and so that might be 1/8 thou at the most. I'm taking about 5. So test cut for the rear corner of the wheel. Now I'm moving into position, and I'll zero it, and now my wheel is located in 2-axis. So you can see I'm at 99.5 thousandths. Once I get to my desired target on the cross feed, I'll feed down to 100 thousandths. And now I can start feeding out, taking a relatively large peel cut. This does prematurely wear the side of the wheel you're feeding with, but it keeps the rear corner, the one you're not feeding with, very sharp. So this L-shaped part I'm working on, I can always have sharp corners, yet not have to make a lot of reciprocating passes. I can more or less just take all the material in one pass. So now I'm doing the next step down. And I'll feed down again a couple tenths from my bottom, and then I'll cut the shoulder. And then I'll feed those last 5/10 to the floor. And now I'll walk off the part, and the part will be finished. So this doesn't give you the same precision level that grinding with multiple spark out passes would, but it does cut very cool, and it gives you enough precision for non-critical surfaces, and it looks pretty good. So now I'm finishing the holes for this. They're 2 6mm holes, and we're just hard milling them in, and we'll fit them with the Deltronics pins. And we're shooting for about 1/10 under nominal, and then we'll just lap that last 1/10 out of them. This machine can generally interpolate around a 1/10, and that's pretty darn good in my opinion. But if I want a smidge more accuracy, I lap. And now we're doing the larger hole that the clamps sit in. grinding the carriage, I made this little construction paper cutout to kind of show the process we used to get all these features cut in. The center powder blue cut shape is the final part shape, and then the perimeters are various levels of stock. So as it comes from heat treat, we have a 5 thou curtain of stock all around it, and we need to remove that and put in these corner reliefs. So we'll start by squaring up the top and bottom, and then the sides. Now those sides are out in air, but we still need it to be square because we're essentially using the part as its own fixture. So we'll get that squared up. Now we have something like this. Basically the corner reliefs and then the L shapes are the only thing with stock left. So once we have that, we could tilt it on a 45 and install the corner reliefs with a V-shaped wheel. And that's really not too complex. And after that V-shaped wheel puts in the corner relief, we have something that looks like this. Just the flats of the corner cutouts need to be removed yet. And to do that, we can do it directly on the chuck, no fixture needed, and we just come in with our wheel and touch and move over, working from the corner out. And that's how you'd grind something like this. It's not too bad when you take it one piece at a time, and then you're left with your final part shape. So now I'm milling the gear rack onto the top of the moving carriage. I was originally going to form grind these, creep feed grind them in with a V-shaped wheel, but it occurred to me I had to stick the part in the mill regardless to bore the 6mm hole for the probe shank, and I almost always have a 0.6 and a 0.4mm ball mill in the machine, which would be the two end mills I needed to machine this. So I thought, why not just hard mill that feature instead of grind it? And it took a little longer than grinding, but it wasn't difficult. So we did as much roughing as we could with a 0.6, just stepping down. And now we're trying to get what's left in the V peeled out, and then we'll use a 3D contour toolpath to do a precision final cut on the V shape. All told, it took about 50 minutes to cut the gear rack, and that probably would have been like a sub 10-minute grind job. So a little bit of a time penalty, but it wasn't my time, it was the machine time, and I'll take that penalty sometimes. This is a brief explanation on how you gauge something like the T shape that's going into the undercut slot. So you need to hold a pretty fairly accurate dimension on that because of the clearances we're running, but you see that the micrometer is kind of an inconsistent way to do it. It tends to rack a little, and you see a little variation in measurements if you do it enough times. So I was getting about 1/10 to 2/10 under 3/8. You could also use something like a disc micrometer, but I find them even worse. So what I do is I measure the position and of the one side, and we're about 1/10 over the nominal size to the CAD model. So I just kind of make a mental note of that. And we're also kind of checking parallelism of each feature set to the other. And now we're going to do what's called up gauge, and we'll be measuring from the underside. And to do that, you just put an additional gauge block on top of your stack to create a ledge, and you set your indicator to that. Unfortunately, I have the dial kind of at a bad angle to the camera, but you get the idea. So we zero out our gauge block stack on the underside, and now we check our part that same way. So if we just barely see, looks like we're about 2, maybe 3/10 less stock than nominal. And so with that 10th extra stock on the other side, that means we're about 2/10 under 3/8, which is kind of in line with what the micrometer was reading. But that's just a little more sure way to do it. Now we're making the small brass gear, which we use to adjust the carriage. I don't do much gear milling, and I don't get to play in brass much, and I had a lot of fun with this one. So I helped out the small tooling I was going to be using by drilling out the root of the gear. I used a 0.3 millimeter drill, and that reduced some of the cutting the 0.3 millimeter end mill was going to be doing later on. So we rough with a 0.8 and then finish with the 0.3. Those are just what I had on hand. Wasn't ideal, but worked out fine. The 0.3 millimeter end mill is a 10 times diameter tool, which is unfortunately long, but it survived just fine. I had it in stock and from an old project and wanted to use it up. Now we are parting off, which isn't something I do a lot in this machine. It's more Haas territory, but it goes fine. I just use a much smaller part off blade, that's all. Now once we get this parted off, we'll have to do something about the 2.5 millimeter hex. So if you're wondering what I'm doing, I decided for the hex it would actually be easier to figure out how to make a broach than rather flip that gear upside down and mill the hex in. I've never made a broach before, but I thought I could stumble my way through it. So I took an old reamer and ground a 2.5mm hex into it, and then I used a 1.5mm wide wheel with an angle, and every 3mm I am putting in a undercut, which the root of measures 2.4mm. So on the part, I drilled it 2.5mm, and there's a 2.5mm pilot on the nose of the broach, and so the undercut of 2.4mm should just be right under that. And I might have gone about that differently if I do that again. I'm kind of winging it here. So now that I have the relief in, I'm switching wheels to 100 grit, and I'm going to put a 5-degree angle on the bottom, and this is going to be the relief angle on the cut edge. And to put the angle on, I'm using my Newbold dresser. So my plan is to grind the last cutting edge in the progression to 2.5mm. Well, it's already there. I just have to get the back taper up to that edge. And once I go around all 6 faces and get that in, I'll move on to the next cutting edge 3mm forward. Only I'll move the wheel down 25 microns, so it'll, well, 12.5, so it'll cut 25 microns smaller a hex. And so with 6 lands, each one cutting progressively 25 microns or 1/1000 smaller, that should adequately make its way up in cut diameter as it creeps through the drilled hole and turns into a hex-shaped hole. Having gotten some use out of this brooch on this project, I really only have 2 regrets. One, the front pilot needs to be much longer. And then 2, there needs to be an undercut shank on the rear so you can push it through. Alright, so I'm sped it up a little just to get through this. So now we're on to the next land, and this one will step down a little. This one will be 1,000 smaller across the flat than the last one in the progression. So I'm just lubricating the broach the best I can, and then we'll give it the old heave-ho. It sailed through beautifully, but each progression of cutting land is only taking 1,000, so you wouldn't expect a lot of resistance. And then just to get the last little bit through, I have to tap it with a punch. So my lack of foresight here was regrettable, but all's well that ends well. Just doing a quick test fit, and I'm not gonna lie, that made me smile. That was a pretty neat little assembly. Gears I don't get to mess much with, so I enjoyed that. Now I need a brass set screw. I thought about just modifying a regular set screw to hold a carbide tip, but I thought holding it could be a bear, and I thought, just as quick I could make one. It only took a few minutes to machine, and then I pressed the broach through it. Now I'll tap the broach out, put my carbide ball in, and press that in, and then I'll grind the face of the carbide ball down, and that'll be the indicator contact point. So this is just a 3mm C2 carbide ball, and then I have 25 microns of interference fit on it. And then I'll grind about 0.5 millimeter off the tip just to make a nice flat land for the dial indicator to push against. So we're getting near the finish line with this machine work on this project. Right now I'm doing some engraving. The gauge bodies and then the 42 and 52 millimeter setting standards all need engraved. When I hard engrave, I use the word engraving loosely. I actually just model the geometry and treat it like 3D contour milling, like it's a mold insert or something. That's just something I've learned having cut enough coining inserts on dies. Really, really hard tool steels don't often work well with the typical tracing style engraving tool paths. So if you treat it like 3D geometry and approach it that way, you get really nice results when hard engraving. Now we got to do some last minute deburring. So it's going to black oxide after this, and if you don't have all the burrs off of it and you try to take them off after black oxide, it's going to look really, really bad. So just take your time and go over everything that's getting coated or oxided, and just make sure it's fully deburred and the way you want it. So I'm using a ruby just to make sure where these two holes intersect that there's no sharp edges that anything can hang up on. And once I've gone through and massaged all those edges, I'll kind of smooth over the corners of the chamfers and the crowns with the belt grinder. And yeah, I'll just take about 20 minutes and go over everything, and then it can go off to black oxide. So everything is back from black oxide now, and one of the things we need to do post oxide is grind the final lengths in on the setting gauges, so 42 and 52 millimeter. And I was happy. My goal was to get it under a half a micron of deviation, and we got that. Now, the ears on the end of the gauge, they have to be coplanar on the top, so I ground them as an assembly. And just to make sure it never gets unassembled and knocked out of coplanar, I'm going to put a little bit of super glue in the cap heads. If it absolutely has to come apart, that's not a big deal. You can pick it out. But it just kind of says, hey, what are you doing? So now we are on to the final assembly. This part's going to be pretty long, about 10 minutes. I won't be offended if you skip through it, but I just kind of wanted to let it play out. I spent a good long while on this project, off and on. I got parts into the machine when it made the most sense and batched stuff up with my regular heat treat. So the project was around the shop for over a month, which is unusual. And so it just felt right to kind of take my time with the assembly and the video and let it play out. So, yeah, and enjoy the assembly and let me know what you guys think. If you liked what you've seen so far, I would appreciate a subscription or a like. It tells me what I'm doing is worth doing, I guess. So if you like it, hit the bell, please. Unfortunately, my phone cut out before I could set the brass screw to 0. But now I'm setting it to the 52 millimeter gauge, and we'll do that by adjusting the movable carriage. This is my first time adjusting this, and one of my design regrets is the carriage actually moves a little too freely, so you'll get it where you want it, then go to lock it up and it'll wiggle off location. So I think it maybe needs like a rubber brake or something to give it a little bit of resistance to movement. It's just too free moving and jumps around, but the amount of disturbance from lockup when you tighten the screw is very minimal, so I was happy with that. Alright, so the gauge is set, and I've machined up a little demo part. We'll see how it works. You rock it to find the low spot. That's where you set your gauge to. And then you compare that to the part. And as we can see, our part is about 6/10 over the gauge. Alright, if you guys made it to the end, I really appreciate you watching. This was a fun customer project, and I was happy to be able to make it into a video. And it kind of lifted my spirits. I was in a little bit of a funk after IMTS, a lot of the same repetitive work, and so I really enjoyed this. And here's the 3D printed gauge I talked about. I wanted to go over this before signing off. So I'm not really going to share the CAD files for this because it really kind of comes down to what indicator you have and the indicator mount. And because of that, if you have like an interrapid and whatever mount, it could be wildly different in proportion than the setup I have. So I'm just going to kind of share my thoughts. I use 3 rods, 2 of which form the base, and then the third rod is just for the indicator to mount to. That chassis concept works well enough. And then on the bottom, I have 2 ball bearings pressed in on this side directly underneath the rod. And it's actually pressed against the rod, and that's to try to give as much stability as possible. And then 1 on the rear, and then the rear fixed contact is what's called a toolmaker's ball. If you search on McMaster, you should be able to find that. And then I ground off about 30% of the tip as to give it kind of a little bit more ability to enter into a shallow bore. Now, I said no machining. I used my surface grinder, but I think you could probably get away with a belt sander or a bench grinder if you had the patience. And then you basically use the indicator mount to fine adjust the depth and position of the indicator needle. And maybe one with a flexure cut that you can creep up on it would make life a little easier, but I kind of wanted to use like a worst case scenario. I wouldn't want to hold tense with this, but if you just need something to confirm a dimension, I like this better than a pair of calipers. And it's, I don't know, kind of a neat little thing to make. So yeah, if you ever need one, just see what you can print up. I was surprised how well it worked. So again, thank you for watching. Have a nice day.